Welcome back, students. I hope everybody went through the first section of this notebook, the review in complex numbers, without much trouble. Now let's move into section 2 of this notebook, the polar form of complex numbers. And as the title suggests, the key idea here is to apply the polar coordinate system to the complex expression z equal to x plus yi, which corresponds to x comma y in the rectangular coordinate system. If we do that, x is r cosine of theta and y is r sine of theta. So x plus yi becomes r cosine of theta plus I times r sine of theta. And consequently, we have the final form by factoring r out and then write parenthesis open cosine of theta plus I sine of theta, parenthesis closed. The final form, r times cosine of theta plus I sine of theta, is called the polar form of the complex number z, or polar expression. And r here is the modulus, absolute value, in other words. It is square root of x squared plus y squared. There's a subtle difference between the polar form of complex numbers and the polar coordinate system, and it appears right here. In the polar coordinate system, the polar distance r could be negative because r in the polar coordinate was not geometric distance, but it was a directed distance. So if you go backward, then you can take negative r value. That's not allowed for a complex number system. R is the modulus, which is always strictly positive, unless of course z is equal to 0, in which case r is 0. Consequently, a little bit of change takes place in the angle as well. By the way, this angle theta is called the argument. It used to be called polar angle for polar coordinate system. For complex numbers, it is called the argument. And the subtle difference is kind of like this. Let's go back to this visualization here. And let's start from the easiest case. This problem is randomized and I would like to get the first quadrant, but I keep missing it. Okay, here it is. First quadrant, this is the easiest case. X and y are both positive, so all you have to do is to take r as square root of x squared plus y squared, which we end up with 1.55386 approximately speaking, and the angle theta is arctangent of y over x. We ended up with 0.384463 pi approximately, but in this case we didn't have to do anything, just arctangent of y over x and we can walk away. But that is not always the case. In this case, we have fourth quadrant. Well, if we simply take the arctangent, then arctangent value can be negative, between negative pi over 2 to positive pi over 2. So we're going to get the angle as negative value. That's okay if we restrict our domain, standard domain of the argument, as between negative pi and positive pi, which is widely accepted too. But most of the time, at least in our textbook, we usually take theta as between 0 and 2 pi. In that case, negative value will not do. So what do? We add 2 pi. We can add or subtract any multiple of 2 pi without affecting the position. So we can freely add 2 pi. And by doing that, you can fit this angle theta in the standard domain between 0 and 2 pi. And that's how we got this 1.53152 pi, which is outside the range of the arctangent function. Now, this is a case when we have the second quadrant here. X is negative. And if you simply take arctangent of y over x, then theta will be negative, and consequently the direction angle will point toward the fourth quadrant. For polar coordinate system, it was okay to fix my direction angle like that and then take negative value as your r and then go backward. You can't do that for complex numbers. R is always positive. So the change must take place at theta. And what changes it? Adding pi. adding another pi, go another 180 degrees, you can go directly backward. That's how we get the second quadrant as the angle theta between 0 and 2 pi. And third quadrant case is pretty much the same. If you simply take, like this, arctangent of y over x, then you're going to get the angle theta pointing toward the first quadrant. And that's not going to be the right one. So you add pi, and what do you get? You get, well, as you can see here, 1.31154 pi. And consequently, we get the angle in the third quadrant. By the way, that's when we have the standard domain where theta has to be between 0 and 2 pi. That's usually the case, and our textbook usually follows that. But in some other circumstance, if you have to put angle theta between negative pi and positive pi, then in this case, in the third quadrant case, we have to subtract pi, and you're going to get the angle theta, which is negative, but between negative pi and negative 2 pi over 2. Between negative pi and negative pi over 2 in the third quadrant. Most of the time, though, we're going to restrict ourselves between 0 and 2 pi. At least that is the case for our textbook. So I'm not going to talk too much about this case, but I do not want to disregard it either, because after all, our textbook talks about this case sometimes too. By the way, here's a summary of some terms. Rectangular form, we mean by z equals x plus yi. Polar form, r times cosine of theta plus I sine of theta, where r is the modulus and theta is the argument. The real part is x, or equivalently r cosine of theta. The imaginary part is y, equivalently r sine of theta. Modulus is the distance from the origin to the point, and it's the absolute distance, the geometric distance. It is square root of x squared plus y squared, and it's always positive. Often it is represented as an absolute value of z. Finally, the argument, theta. There's a little bit of difference between the polar angle and the argument. We talked about it, and that is coming from actually the modulus, which is always positive, compared to the polar distance, which could be negative. Did I say finally? Well, I'm sorry, one more to go. Conjugate. And z bar is x minus yi. That is, if I change the sign of the imaginary part, and we get the conjugate. Geometrically speaking, we have to get a point symmetric to the x-axis. So we just flip the given point to the other side of the x-axis. But equivalently speaking, we can write it in polar expression like this: r times cosine of theta minus I sine of theta. That's easy to see. Change of this plus sign from here, the polar form, to this minus. Now here is an ingenious observation. Cosine of theta is the same as cosine of negative theta, so replace theta by negative theta without any change. Now, sine of negative theta, on the other hand, is negative sine of theta. So if I replace this theta here in the highlighted expression to negative theta, then I have to change this into plus form. So what do we get? If you conjugate, it's equivalent to changing the angle theta to negative theta, because the final form is another polar form, because this is plus now, except the angle is now negative theta. So there are two ways to get a conjugate. One is to change the sign of the imaginary part. The other is to change the sign of the argument, the angle. Okay, let's breeze through one more expression of polar form, and then let's have a little bit of exercises. An advanced form of polar form is like this: r cosine of theta plus I sine of theta can be rewritten as r times e to the I theta power. Why? Well, that's a good question, but we're not ready to answer that yet. As a matter of fact, we will answer that question in Calculus 2, so please be patient. But it doesn't mean that we are not allowed to use it yet, because it is true. We are not going to prove it. We are going to prove it in calculus too, but still, let's just use it. If we do, then we can have some interesting things like multiplying two complex numbers in polar form can be, let's see, R1 e to the I theta 1 times R2 e to the I theta 2 can be written as product of the moduli and the sum of the arguments. Because arguments go to the power, so the base is the same, natural exponent e, so multiplication becomes the addition in the power. How about the division? Division is actually inverse operation of the multiplication, so we expect the inverse. Indeed we do. R1 e to the I theta 1 power divided by R2 e to the I theta 2 power is the same as R1 over R2. Yes, that's natural. And then e to the I theta 1 minus theta 2. Yes, that's because division becomes subtraction if you go over to the power when we share the same base. If you repeat multiplication n times, we get that r times e to the I theta power, to the nth power is r to the nth power times e to the I n theta. So all these can be derived very easily if we accept this advanced polar form. Proving this advanced polar form is a different issue. We're going to do that in Calc 2. By the way, the most interesting case appears when theta equals to pi. When theta is equal to pi, then plug into theta equals to pi. What do you get? R is 1, theta equals to pi, so e to the I pi is cosine of pi plus I sine of pi. But sine of pi is 0, isn't it? So I sine of pi, that part is 0, so that drops out. Cosine of pi is negative 1, so negative 1. So e to the I pi is equal to negative 1. So if we flip negative 1 to the other side, then we are going to get this relation here. 1 plus e to the I pi power is equal to 0. And this identity is also called Euler's identity. There are so many Euler's identities out there, and this is probably the most famous one. And actually this one, cosine of theta plus I sine of theta is equal to e to the I theta power. That is also called Euler's identity. There are many out there actually, because Euler did so many things. Anyway, the final form here, 1 plus e to the I pi power equal to 0, is very interesting in the sense that it gives you a relationship between arguably the 5 most important numbers in mathematics, 0, 1, pi, e, and I. Those are all here, and we have extremely simple identity. That's where mathematical beauty comes. Well, let's see. We have sufficient time to do one type of exercise, example 2.3. This is rather trivial, changing polar coordinate to rectangular coordinate. So if we know the modulus and the argument, how can you find out the rectangular form? Just do the computation, cosine of 7 pi over 6 and a sine of 7 pi over 6, this and that, and then distribute the modulus, and then we have the answer. Just trivial. Here's a second problem, again equally as trivial. Just calculate cosine of negative 2 pi over 3 and sine of negative 2 pi over 3, and we did over here. And then distribute 2, and we get the answer. How about this problem? This looks a little bit more intimidating because we use the advanced form, but that's no problem at all because e to the I theta power is nothing more than cosine of theta plus I sine of theta. So if this is the same as 4 times cosine of theta plus I sine of theta form like this, and all you have to do is to calculate this cosine of negative 2 pi over 3 and sine of negative 2 pi over 3 right here, and then distribute 4, and then you have the answer. That's the final problem is done pretty much the same fashion. This is not a basic angle, so you may have to use calculator. If you use symbolic computation, by the way, it will have something to do with square root of 5, but it doesn't really matter here. All you have to do is calculator, and then that's it. Distribute out, and that's it.